A system of two non-interacting identical bosons is in thermal equilibrium at temperature T. The particles can be in one of the three states with the non-degenerate energy eigenvalues minus epsilon, 0 and epsilon. The temperature T is such that e to the power exponential minus epsilon over kBt is equal to half, where kB is the Boltzmann constant. The average energy of the system is found to be uh, the minus n by 35 epsilon. So this is the average energy when you calculate it, where n is n is an integer. What is the value of n? So the question is, what is the value of n? So the average energy expression is given by minus n over 35 epsilon, where n is an integer, and one has to calculate, one has to determine the value of n. So what we do is, we find the number of accessible microstates of the system. We have two particles and three energy levels, minus epsilon, 0 and epsilon. And these are the possible states of distribution. Here we can see the two particles in the energy level minus epsilon. So their total energy is minus 2 epsilon. Here the two particles are in the energy level 0. Since the two particles are in energy level 0, their total energy of the system is 0. Here the two particles are in energy level epsilon, so the total energy is 2 epsilon. And in this way, we have here one particle in energy minus epsilon and the second particle in energy 0. The total energy is minus epsilon. And here we can see one particle in energy epsilon and another particle in energy minus epsilon, so total energy is 0. And here we have one particle in energy epsilon and second particle in energy 0, so total energy is epsilon. So these are the possible microstates of the system. And we can see that all these energies, whether it is minus 2 epsilon, minus epsilon, the degeneracy is 1, but for 0, 0, the total energy 0 comes for two distribution. This distribution has total energy 0, this distribution also has total energy 0, so the degeneracy is 2. So the degeneracies are given like this. So these are the possible energies of the system and these are the corresponding degeneracy. So to calculate the average energy, we determine the partition function. So what is the partition function? Sum over all states of this factor. Okay, so what we get is this, and here we have 2. This corresponds to the degeneracy 2 of the energy level of the total energy 0. And this is what we get for the expression for partition function. The average energy is calculated from partition function using this expression minus dou by dou beta of log q. Beta here, it is 1 by kt. Beta is 1 by kt or 1 by kbt. This is beta. So we are taking the dou by dou beta, the negative dou by dou beta of the log of the partition function. Okay, and we follow the differentiation. As you differentiate, you will be getting this. Log q. As you differentiate, q comes in the denominator, and the numerator you have dou by dou beta of this. And as you differentiate, you will get this expression. Also, in the problem, it is given that the temperature is such that e to the power minus epsilon by kt. E to the power minus epsilon by kt, that is equal to half. Okay, e to the power minus epsilon by kt is equal to half, or e to the power minus beta epsilon is half. Also, e to the power beta epsilon is given by 2. Okay, e to the power beta epsilon is given by 2. Okay, so we substitute all these things here. As we substitute, we get this e to the power minus beta epsilon half, e to the power beta epsilon 2, that you substitute, and you finally get this result. The result is this: minus 36 over 35 epsilon. And as we compare this with the result given in the question, result given is minus n over 35 epsilon. So this epsilon is now 36. Okay, epsilon is 36. Sorry, the n is small n is 36. So this is the result.